So hello everyone, my name is Vikas Soni and today we are going to talk about the bit manipulation. So this playlist is going to be a list of three videos and in these three videos. So in the first video we are going to talk about the fundamentals of bit manipulation, right? All the fundamental functions and the things that are used in the topic bit manipulation and comes in the questions of Codeforces or any other platforms. Okay, and we are going to talk about the thinking approach for solving this bit manipulation questions, right? Because like for the graphs, graphs or other things, you just have to learn some fundamental algorithms. And after you learn this all fundamental algorithms, you can solve like 80% of the graph question. But in the bit manipulation, the thing is not like this because there are no such fundamental algorithms you can learn, right? Of course, there are some of the fundamental things like what are bits, some functions of bits like XOR or an and some of the observation on this, but there are no such algorithms that you can just learn and solve all of the question of the bit manipulation, right? But in this, what you should have is the clear thinking approach, right? You have some question and you have some problem, and then you you should take some observations, and from based on these observations you can come with some pattern, and that's how you solve the solution. And like we will see this in next minutes. Okay, so this thing we are going to cover in the first video. Now in the second video we are talking about using bits as sets. Now you know the sets, which are some just a bunch of some elements are sets, and we can also do some operations like union, intersection, adding two sets, and minusing one set from other set, and subset, superset, and all of this thing. So we can do all of these things in us by storing them as bits, right? We are going to talk about this in the next video. And also the most important thing it is we are going to talk about the list of the patterns. So like there are such fundamental observations in the bit manipulation thing, and from this we get some patterns, and by some like by some 20% patterns, the 80% of the questions are going to be solved. So this will be going to be the most important thing in our series. And in the third video we are going to learn about one important data structure, which is binary trie. And also in the third video we are going to solve some of the crazy problems, and in these problems that are going to be greater than 1600 rating, and with these problems you will you will learn that how to solve this question and how to ask the questions for the, like you have some problem and how to ask some questions to yourself, like is there some limit on the question answer, or how the question, how the answer should look like, or how the mm, okay, sorry. And and you will learn that step by step in the third video, right? So let's start with the fundamentals of bit manipulation for CP. Okay, so in the most fundamental thing in this bit manipulation is going to be bits. So we should ask ourselves that what are the bits. So as we know that the computers cannot store the numbers and the data, they know only zeros and ones. Yeah, we are teaching this in the colleges and schools. Okay, so this series of 1 and 0 are what we call the binary numbers, or what we call the bits in this case. Okay, and how does the bits and this binary numbers look like? Hmm. So let's just talk about this. So we know that binary numbers are nothing but just some, like we just store them like this, like some a some number a, which is going to be 0 or 1, into 2 raised to power 1, plus b into 2 raised to power 2, plus c into 2 raised to power 3, something like this. Okay, this thing is what we call a binary number. So, yeah. So like let's take some example. So let's take we have some number 101. This number is 101. Now the rightmost bit is always represent 2 raised to power 0. And the next bit, which is 0 in this case, shows us represent us the 2 raised to power 1. The third bit, which is like the bit shows us the 2 raised to power 2. So like in this case, the bit which represent this 2 raised to power 2 is 1 in this case. So the answer is going to be something like 1 into 2 raised to power 2. So that we know that the the value 2 raised to power 2 is present in our decimal number. Then plus the number that represent the 2 raised to power 1 is 0. So we just do 0 into 2 raised to power 1 and then 1 into 2 raised to power 0. So this 101, this number 101 stores the decimal number 5. So this was just the code of the bits. Okay, if you don't know what are bits, you can learn them in the some other videos, right? Because this thing is not much used in this in the CV, right? This theory is not that important. So what is the important thing? So there is going to be some of the huh, what we guess some representation. Okay, so let's say we have this bit. Okay, we have this bit, so we know that this bit is nothing but this thing is 0. So okay, let's write here. Just say, okay, this thing is going to be 1 into, so this, we know that this bit represent 1, this bit represent 2, this 4, and this 8. This is going to be like 1, then 0 into 4 plus 1 into 2 plus 0 into 1, which is going to be 8 plus 2, which is 10. Okay, so let's say we have this number 10. So now, this rightmost bit, this rightmost bit in this thing, in the binary number, the rightmost bit which represent 1 is the smallest bit, right? Is the smallest bit. So the thing you have to remember is that the rightmost bit is the smallest bit. Then we go in the left. So that's how we store the numbers. Okay. Mm, Now the important point is LSB and MSB. Okay. So now what is the LSB? What is LSB? So this thing is called least significant bit. Significant bit. What do we mean by least significant bit? So this means is the bit which have the least significant. Okay, just joking. So LSB means the rightmost bit which is 1, the rightmost bit which is 1. And what do we mean by the rightmost bit? So the smallest thing, the smallest is value, the smallest is bit. Okay, this thing is 0th bit, this thing is first bit, this thing is second bit. So the smallest bit which has this value 1. So like let's take some examples. So in this value, the LSB is equal to 0 because this 0th bit is 1 in this. Let's say in some number 1001000, the LSB is going to be 0, not 2, this, sorry, not 0, not 1, but this 2, because the second bit is the rightmost bit in this whole number, which is 1. So this LSB is going to be 1 in this, 2 in this case. Let's just take some last example, which is, let's say, 1000. Then in this case, the LSB is going to be like 0, 1, 2, 3, 4 and this 5. So the rightmost bit, which is 1, is the fifth bit. So LSB is going to be 5. And don't ask that what will be going to be LSB for this number. So this thing is not defined for this, not defined. We only care for LSB when the number is greater than 0. Okay, and the other important thing is MSP. What is MSP? This is just reverse of this LSB, which is most significant bit. Most significant bit. And what do we mean by the most significant bit? So the bit which has the most value. And let's say, or the leftmost bit in the binary value, binary representation, right? The leftmost that bit, or let's say more leftmost bit, which is 1. Okay, which is 1. So let's say 10010. In this case, the MSB is just the leftmost bit, which is 1. So this is this bit. And this bit is 0, 1, 2, 3, 4. This bit is the fifth bit. So MSB is going to be 5 for this. What about this number? So 0, 1, 2, 3. MSB. Oh, sorry, I just did a small mistake in this. 0, 1, 2, 3, and this is the fourth bit. Okay. In this case, the MSB is going to be this bit. And what is this bit? So this bit is 0, 1, 2, third bit. Yeah, this is the third bit. So MSB is going to be 3. So these were two important things, two important words that get used many times in the bit manipulations. Okay, but this was just a basic thing. Now come to the main part of the bit manipulation, like most fundamental things of the bit manipulation, which are bitwise operations. Bitwise operations. Now there are some bitwise operation. One is the first one is bitwise AND. Now, what are some the bitwise operators? So these are just some, like you can say, some functions where you give some numbers, some binary numbers, and in return, you get some, uh, you get a binary number, right? A one binary number. Okay, so this is just like some, we do some operations on the binary numbers, and then we just output the results. That's that is the binary bitwise operations. So let's see this by the example of this and. Now this and just shows that. So okay, just a second. Okay, so in this bitwise operations we have to go for bit by bit, and for every bit, for every bit, the result is one if in every number we have, the ith bit is like, or in every number that bit is 1. Like, what do I mean to say is that, let's say we have some example like 1101 and 0001, or let's say 111 or 1001. Okay, now we will work by bit. Okay, we will work bit by bit, and you know that we just, so there is, you can think of this is like we just input this in this box, in this black box, and we are going to get some result. Okay, some result, some result. Let's say this as re, and this thing is bitwise and. This is just a symbol of AND operator. Okay, so how the how this machine is going to work is something like that. We will see both bits, right? Okay, so let's say we just see the case of the third bit, and in this we just say that if all of the bits, if so, I'm sorry, if in all of the numbers, if this bit is going to be 1, then in the result that bit is going to be 1. So like for the third bit, we say that is in all of the numbers is that third bit is 1 or not. So we can say that yes, in this number this is also 1. In this number this is the third bit is also 1. So therefore in result the third bit is going to be 1. Okay, so there is like the four values, right? Third bit is going to be 1. And what about the second bit? Okay, so we just see all of the bit, or I'm sorry, we just see second bit in all of the number and ask them that what is the what is the like how many, oh I'm sorry, is that all the numbers have this second bit is equal to 1 or not. Okay, so we will ask this number that, hey, do you have the second bit as 1? He will say yes. And we come to this one. We will ask that, do you have the second bit is equal to 1? And this will say no. This number does not have the second bit is equal to 1, and therefore this thing is going to be 0, because we know that all of the numbers should have that ith bit is equal to 1, right? Like we will ask this bit that, do what is your first bit is equal to 1, and he will say no. And I know that I don't have to see the all of the other numbers, because I know that every number this bit should be 1, and there is this bit is equal to 0. So this thing is going to be 0. We will ask this one and this one, so both are 1, so therefore this is going to be this. So therefore we can say something like that the AND operation of these two numbers, we get 1001. Let's try this with some bigger number, okay? Some the list of more numbers. So let's say 1101, then 1111, then let's say 101101001. Okay, so let's say, okay, now what would be the end of all of this? So this is the result. Let's say this is the end of all, and we know that there will be 4 bits in this. And now we will ask that we will see for the fourth bit. I'm sorry, third bit. So we will go and ask all of the numbers that is the third bit set in all of these numbers, and all of these numbers will say yes. The third bit is set in all of these numbers. So therefore, because this thing is set in all of the number, this third bit is going to be 1. Let's come to this second bit, and we will ask this bit that this number that what is your second bit. He will say 1. I have this bit as 1. Okay, so we just move to the next bit. We ask this number that what is I mean is your second bit is 1. He will say yes. We will come to this bit, this number, and ask that is your second bit is 1, and I will say no. And just at the point we hear no, we will just make this a 0. Just do this for again, and this thing would be 0, because the first bit is 0 in the first number, and for the 0th bit we know that this thing is 0, so therefore this thing is going to be 0. So this thing is, it is easy. Like if for every bit, if it is 0 in any number, then In result, this bit will be this bit equal to 0. Else, else this bit is equal to 1. That's it. So this thing was for AND operator. Now let's get to the next operator, which is going to be OR operator. But okay, just before going to this OR operator, let's say about some properties of this AND. Okay, what is the properties? So with any number, if I do this, it's AND with 0, then I'm going to get 0. Like I have some number which is this, and this is 0. Okay, as we know that the binary representation of the number 0 is this thing. Okay, all of the numbers are going to be 0, and this is some number. I don't know what it is, and we do AND of this. Okay, we do AND operator on both of these. Then we know, sorry, bitwise AND of these two numbers. Then we know that when we are going to ask our question that, hey, is the ith bit is 1 in your case or no? And if we hear no, then we just make that bit 0 in the result. But you know that because this all of the bits are 0, then I know that therefore in result, no matter no matter what number this is, this thing will make my result is equal to 0. That's it. So this was one property. Now we know another property is A and A is equal to A, right? Sorry, is equal to A. Like 101 and 101 is going to be, so we will ask this number that is your second bit 1, and this will say yes, then 0, then 1. So this result is the same as the bitwise, uh, the result of the bitwise AND of these two numbers is the same as this number itself. That was a property. Okay, and the next thing is bitwise OR. And in this bitwise OR, the definition is like the OR sets a bit to 1 if any of the bits is 1. That's it. Okay, so the definition of this AND was something like this AND sets the number equal to 0 if any of the bits is 0. So that's it. So in this OR, like what is going to be like the truth table for it? So like we just have one bit. Okay, we are just going to see for one bit, and let's say if the both bits are 0, then 0 or 0 is going to be 0, then 0 or 1. So we know that at least at least one bit. Okay, any one of bit is going to be 1, then the answer is going to be 1. Then 1 or 0 is going to be 1, and 1 or 1 is going to be 1. Okay, sorry if I said zor in this, and 1 or 1 is 1. That's it. So this is the thing. Now let's take for some big binary numbers, how is this going to look like? So let's say I have one number which is equal to 5. The binary representation of 5 is going to be 101, which is 4 plus 1. And the binary representation of, let's say, 3 is going to be 011, because it is like 2 plus 1. Is that clear? So now what would be the OR of these two numbers? So we will just go bit by bit, and let's say this number is 1 and this number is 0. So 1 XOR 0, which is 1 in this case, 1, and 0 or 1, 0 or 1, which is 1, then 1 or 1, which is 1 again. So the OR is going to be 7 in this case. Okay, in our case, okay, this is equal to 7. So this is how OR works. But if there are more than two numbers, what if the number is something like this? Oh, sorry. Then we will just traverse in all numbers, and if any of this bit is 1, then the result is equal to 1. That's it. That's very simple. So like we will go into this thing and check if any of one the bit is 1. So this is 1, and we will just check in those bits, in the second bits, and if any of this is 1, yes, and this is 1. Okay, just a second. We will then just see that is any of this is 1, and yes, if at least there is a 1, then again the result will be 1, and we will check that if any of these numbers is 1, and in this case there are no ones in the first bit as in the 0th bit, therefore this thing will be 0. So that's it for all. Okay, now the properties of this are like with a or with 0 is equal to going to be a, and a or a is going to be again a, right? That's very easy. Now that we discuss about the most important bitwise operator which comes in the majority of the questions in the bit manipulation, which is bitwise XOR. XOR. Wait, bitwise XOR. Now, what is the bitwise XOR? Okay, so in the result, in the result, the bit is going to be 1 is going to be 1 if if uh, if both bits are different. So this is for the two numbers. Okay, so if the both are different, then the result is going to be 1, else this is going to be 0. So let's take for 0 XOR 0, which is 0, because we know that this both bits are not same. Okay, are same, are not different. Then 0 XOR 1, so they both bits are different, therefore this thing is 1. Then 1 XOR 0, it is also 1, and 0 XOR sorry, 1 XOR 1, which is 0 in this case, because this both bits are same in our case, right? Okay, just a second, I just forgot to write the I mean there. Just a second. Okay, nothing. So this thing shows the XOR, right? So this was it. And what if there are more than two numbers? Okay, what if there are more than two numbers? So okay, before this, we just check for the two numbers. Let's say we have some big two numbers, something like this. Then what is the result is going to be look like? So this fourth bit, we will just count how many ones are there. So you know that there are two ones which are same. So we know that 1 or 1 is going to be 0. Check for this two. This both are 0. Then this thing is going to be again 0. This both numbers are different. Therefore this thing is going to be 1. This both are different. Therefore this thing is going to be 1. And this two are different. So therefore this thing is also going to be 1. So that's how you count the or you find the XOR for two numbers. So by this we can say that 10101 XOR this number is going to be equal to this number, right? Now what if there are more than two numbers? So you will count the number of elements which have this ith bit set. Okay, I mean what I'm trying to say is that let's say we have some numbers like this. uh, okay, and we know that in the result it is going to be something so like this. And for this third bit, we will just count that how many elements have this third bit equal to 1. Okay, how many elements, let's call it num3, which is how many elements have this third bit equal to 1. So 1, 2 and 3, three numbers have this. What about the num2, which is how many numbers have this? Okay, I'm sorry, this thing is num4, right? This thing is num3. So then we will ask that how many numbers have this third bit is equal to 1. So this thing have the third bit equal to 1. Yeah, only this thing. So this thing would be num3 is equal to going to be 1. Then num2. We will again ask that how many numbers have this second bit is equal to 1, and in this case there are 1, 2 and 3 bits, right? So this thing is going to be 3. Then something like this, the num1 is going to be 2 and the num0 is going to be 1. Now, now the ith bit, it, ith bit is going to be 1 if the num I if the num I is odd, if the num I is odd. Okay, so like what will be this fourth bit? So we will check at the num4, which is 3, is this odd? And yes, is this is odd, so therefore this bit is going to be 1. Then this bit is odd, so this is going to be 1. This bit is odd, so this is going to be 1. This num I, which is num1, which is the number of elements which have this first bit, is equal to 1, is 2 in this case, which is not odd, so therefore this thing is going to be 0, and this thing is going to be 1. So from that we can say that the XOR of this four numbers is going to be this number. So let me just discuss about like the properties of this XOR. Okay, so the properties of XOR are very very important. Okay, so the XOR of a element two times is give us 0. So if this property is kind of very very useful to just find if duplicates are there or something. Okay, so now it's something, we have something like a XOR a, oh sorry, a XOR a XOR b. Then you know that these two XOR are going to be cancel each other out, and in the result I'm going to have only b, right? So that's it. So this property, this cancelling property, is very very useful in the XOR questions. Okay, another thing is XOR of a with a 0 is going to be a. Okay, because that's easy, you can see this thing, right? So this was all the fundamental bit manipulation operators, right? So in the majority of the question you are going to see only this three of thing. Okay, there is also a NOR one. There are also like very I'm sorry that there are some like X NOR and something, but they are not going to be used too much in the competitive programming one, so you can just don't learn that now. If in some question they are coming, then you just learn that thing, right? That's very easy. Then some functions are like twos twos complement, and that thing also, like, this is not much important. Like, I have never seen any question of this twos complement in my like 1.5-year journey of competitive programming, so this doesn't use very much in, right? Okay, now this is these are the main operators, okay, of the competitive programming. Now let me say how, let's say some cool function, okay, some cool functions That will be helpful. Okay, that will be helpful. So these three operators are the inbuilt one. These are from C++, but or any language. Okay, but now there are some of the things that we use, right? So like let's say first thing is like how to print the binary representation, how to print the binary representation of any number. How do we do this? Do this. Try to think of this for a minute. And okay, so I hope that you think some time on this. Okay, now this thing is very easy. So there can be many approaches, right? So for this, like you will iterate from MSB to LSB, right? So what do I mean is like you will go iterate from the leftmost bit to the rightmost bit. So okay, let's assume that the most of the numbers in the programming, like you use only int and you use long in some cases. Okay, so this integer stores the bit of 32 and long has maybe around 64 bits, right? So what you will do is you just do you just run a loop from the 32 to till 0, sorry, till 0, and then what we can do is if the ith bit is set, if the ith bit is set, then print 1, else print 0. So this thing also can be used in this, but now the question remains, how do we check that if this ith bit is set or not set? Okay, so for this, just don't see. Okay, for this, let's see. Our second question is checking check if ith bit is set or not. And by set we mean that if the ith bit is equal to 1 or not, right? So how do we do that? Okay, how do we check? So that is easy, but before that you have to learn a small thing, right? You'll have to learn the shift operator. Now what is the shift operator? So assume that there is some number like this, then shift operator. So there are two shift operator, one is left shift and one is right shift. Okay, so one shift operator is this one, which shift, you can just say that uh, this shift the value in left. Okay, what do I mean by this is like we use something like we have some number which is this one and we shift this by 2 times, then the result we are going to get is 10 1 0 1 0 1 0 0. So you can see that. Okay, just a second. This was a number, so you can see that this number is now shifted in the left side, and now the some zeros, two zeros are added in the right. This is it. And the right shift, this thing shift the value in right. And how do it shift in right? Let's say again we have this thing, we shift this by 2. Then now this all values are going to be 2 times in right, so these two values are going to be deleted. This one comes to the first place, this 0 comes to this second place. So all the values are shifted in the right, and it doesn't matter for these elements, right? These things are just going to be deleted. So now in this our value will be now 0, just a second, 1 0 1, yeah, that's it. And there are going to be some zeros in the left. So this, as you can see that this thing is now shifted. So in this, can you see a thing? Can you see the important thing, right? That is that if I shift by ith number, the ith bit now comes to this point. So this was the thing. So You can, this thing is useful in checking if the what do you say, if the ith bit is set or not. Now, how do we check this thing? Okay, so this thing is just, we will check that. So first, let's say we have to check for the nth number. So what we'll do is shift this n, right shift this n by ith point, and then just check end with 1. Okay, now let me be like think at this clearly, that what do this expression mean in this. So we know that we have to check for the ith bit. Okay, so what we do is we just right shift it I times. So let's say the number was this and we shift this by 2. So now my number is going to be 1010. That's it. So now you can say that ith bit is now came to this 0th position. Like, is this understandable to you? Like I have to check the second bit, right? So I right shifted by 2 points, and now this 0 what I have to check comes to this point. So now I know that I have to check if this point is 0 or not, if this bit is 0 or not, and that is just I do it with and with 1 and with 1, right? So now like let's say I just do it's and with the number 1, and now I know that if this is 0, if this number is 0, then I'm going to get this point. And or if let's say this thing is 1, then I'm going to get 0 0 0 1. So which is, this thing is nothing but 0 and this thing is nothing but 1. So that's how we can check. Okay, if there is some other way, what is the simplest way? Okay, let's say some, let's try to think for some simple way. And let's say the number is something big like this, and I have to check if some number, like say this is the fourth bit, this fourth bit is 1 or not. So what can I do is I can have some number which is just this thing, and now I will just check end of this with this number, and so this thing is nothing but if this n and the one shifted I times, and if this is 1, then this bit is set, else this bit is unset. So that was it in this question, right? So this thing we used to check if the ith bit is set or not, and in this question where you have to print the binary representation, you will just call this function or just write this if condition here, right? And then you are going to print this. Now, how to check the, okay, just a second, this is our third function, right? How to check the, okay, how to find the number of set bits, number of set bits. So this is also easy thing, like you can just print or have its binary representation in the vector, and then you can just count in the array, or you can just copy paste this thing, and if the ith bit is set, then you will do count plus plus. So this is very easy thing, right? So this thing can be used in, like, this function can be used in many of the questions. Okay, and for doing this thing, there is also inbuilt function in the C++, which is built-in pop count, right? Pop count. And if you are using long, then you have to do this thing. Okay, and here just comes the number, which is n in our case, right? So that's it. So this thing can be also be used for finding the number of set bits. Okay, so I hope that this thing is okay to everyone. Now, how to modify this thing? Okay, now this thing is about oh, sorry. Now what we'll do is modify the things. Modify of function, right? The function that modify something. Okay, so now how to just set the, this is the fourth function, which is set the ith bit. So now we know that to set something we use XOR. Like how this thing will work is we will just do we will do just this thing, okay? uh Something like a is equal to a XOR or the one shifted left shifted I times. So that's it. So now we don't care about the one in this a, okay? We don't care if it is, the ith bit is 1 or 0 in this a, because we know that the ith at the ith bit, this number will have the ith bit is equal to 1, and this whole operation is in the resulting array, the ith bit is going to be 1 in the end, okay? So that's it. Now how do we unset the ith bit? How do we unset the ith bit? So this thing is can be done easily by the this thing like a and not, and this is just one zord, oh, sorry, one, this shifted that much time. But you don't have to learn this NOR thing because this thing is not that much used. So you can just remember this thing, or what I do many times is find if the ith bit is set. Ith bit is set. Because if the ith bit is not set, then we don't have to do anything. This is already unset. If this bit is set, then just do a is equal to a minus 1 shifted I times. So that's it. So that is like the easy thing, and you can also understand this thing easily. Right? What we are doing is just minus the value of that bit. So therefore the this one is now going to be 0. So that's it. So now some points is that this bit manipulation thing is applied at like the low level thing, okay? Low level thing, and are faster than arithmetic operation. So at any point there are some option to use arithmetic or bit manipulation. You must choose the bit manipulation, right? So like if at some point you have to do like a is equal to a into 2, but now you know that you can do that by just a and just shift by this by 1 point, right? Because you know that the one time shifting is just multiplied by 2. So you should choose this point. Although this will not help much in the competitive programming, but in the like in the big companies where every millisecond is important, you should do this thing. Okay, so this is the good approach to do this thing, do the operations like this thing. Okay, now also the how to find the MSB and LSB. So this thing is like easy. You just loop from left for like for finding the LSB. You just loop from right, and the first bit and the first bit, which is 1, is your LSB. And for the MSB, this thing is same, but you just loop from right. Loop from right. And what do we mean by loop from right? So like in this, you know that you are going to do this thing. I plus plus. I don't care much about this middle, or you can just say here I is less than 35. or like 64 in the case of long long. But in the loop from right, you can do something like for I is equal to 35, or usually you can just do 64 and use long long everywhere. This is like the better way until I is still 0 and I minus minus, and just you just check if ith bit is set, then you just print it or have it somewhere and just break the thing. Okay, then do your work and just break it, break the loop. So right, okay, so this thing was also like very important function. So this thing comes like very much while solving the questions, and in the CF these are used very much. Okay, so like even if you just learn the logic, but still you cannot know that how to set this weight, you cannot solve that question, right? So this thing is very very important and everyone must know this tricks. Okay, now let we, I guess this was all the fundamental things in the bit manipulation. I just forgot one two things. Okay, now there is also some short trick for finding the range XOR. What do I mean by range XOR? Is, let's say you have to find the XOR of this thing like 2, then XOR 3, then 4. Okay, not this, let's say 1 XOR 2, XOR 3, then 4, then 5, till let's say 10. Okay, now you have to find this XOR. So for this, either you can just loop and do this thing, which will be O of n. You can just use this formula, which is if the nth number, you just count its mode 4. So in this case 10 mod 4 is going to be 10 mod 4 is going to be 2. So therefore the result is going to be n plus 1, which is 10 plus 1, which is 11 in this case, right? So that's how you can find the XOR from 0 to any other element. Okay, any continuous segment. Now let I ask you some question. How to find the XOR from L to R? This is also a fundamental thing. Okay, how do I XOR from L to R? Let's say for example, XOR from 3 to 6. 3 to 6, which is 3 XOR 4 XOR 5 XOR 6. Without having this O of n loop, how do you going to find this thing? So like from this formula, you know that we can get the XOR of, let's say we can get the XOR of this thing, but now we want from 3 to 6, from 3 to 6. So the answer is like, it is very simple. It is just the use of the important observation of XOR. So let's say that I know the XOR of 1 to 6 and also the XOR of 1 to 3. And now if I do the XOR of this 2, I know that this 3 is gonna cancel this 3. This 2 is going to cancel out this 2, and this 3 is going to be cancel out this 3. Oh, sorry, I don't have to use 3 here, sorry. So like I know that how to find the XOR of this term in O of 1, but I also know that this 1 and 2 like they are the extra terms. I don't want them in my XOR. So therefore I will just find the XOR of 1 to this thing, which is 1 to L minus 1 in also O of 1, and just do the XOR of these two terms, and I know that this 2 is gonna cancel out this 2 because we know that 2 XOR 2 is going to be 0. Right, so now this 2 will going to be cancelled out this 2, right? And we will get this thing. So XOR from L to R is just f of L minus 1 XOR f of R. Right, that's it. So this thing is like also somewhere we used, and there are some other important function which are inbuilt in the C++ library. Okay, like this thing is just give us the number of zeros at the beginning of the number, this thing at the end of the number, this thing just returns the number of ones, and this thing just the parity, which like this thing is just the will give us the sum, like count how many bits are one and then return its parity. Okay, so I hope you just understand this fundamental things, and I guess now we should move to the sum of the question. Okay, right. So let's read this one. It is the easy one question, 1000 rated. So in this question, like you are lover of a bacteria, you want to raise some bacteria in a box. Initially, the box is empty, so there are zero bacteria in this. And each morning, you can put any number of bacteria in the box, any number of bacteria in the box. And each night, every bacterium in the box will split into the two bacteria. And you hope to see exactly X bacteria in the box at some time. Okay, so like let's try to think for this question. Okay, so what are the observation we get in this? So we know that all the bacteria, all the bacteria will get multiplied by 2, multiplied by 2. So assume that the number of bacteria is equal to 5 at some point. So after one day, the number is going to be 10. And also, like, the thing is that it is multiplied by 2 can give us some hint that there can be binary or a bit manipulation is used in this thing. But like, although this doesn't give the surety, but now let's try to take some observation. So assume that we don't know anything in this. So let's take some test cases. Okay, test cases. So what if there is only one bacteria? So you will add one bacteria only, and then in the box there will be one bacteria. So answer is just one. What do you do for the two? So either you can add two bacteria on day zero, or you can add one bacteria on day zero and wait till day one, because then at the day one, the number which is number of bacteria on the day zero which were only one into multiplied by 2, and we get 2 in this. Okay, so we know that waiting is the better option in this. Okay, but how much we can wait and how should we wait? Let's say we have 8. Again, we know that we will add 1, and then on the first date will be 1, and second date will be 2, third date will be 4, and 8. So in this, one observation we got is that we get the power of 2 in just one operation, or in just one bacteria, right? Hmm. So now you know that we get the 8 with just one bacteria, right? Can I get 9? So how to get 9? How to get 9? Okay, so we are just taking the easy test case which we can just solve by hand. Okay, so we have to get 9. So one approach can be one. There can be many approaches. Okay, like you just add 9, which is 100% wrong. You can you can do something like add 1, then make it 2, then make it 4. Sorry, add 1 in the first day, then you know that at the second day they are going to be 2, on the third day they are going to be 4, and then you know that they are become 4. Then you just add the 5 in this. So that can be a way. Or you can just wait. Yeah, you can just wait for now, and let's say now they become 8. And after they become 8, you just add 1 in this. Add one bacteria, on the day on the day 4. Okay, so this was day 1. So you add one bacteria on the day 2. You do nothing, sorry, you add one bacteria on the day 1. You do nothing on the day 2. So now this thing go multiplies by 2, and this is 2 now. Then again, sorry, you do nothing on the day 3. So the bacteria on the day 2 multiplies by this and now becomes 4. Then again on the day 4, this bacteria has become 8, and now you just add one bacteria with your hand. Okay, so the number of operation is 2 in this case, right? So like okay, let's try to have something else. What will be the case of 10? So you can do the case of the similar like we did in the case of 9, but in the end we can just add this 2 here, right? Add this 2 here. But in this, you get a really like important observation is that instead of adding this, okay, let's just make some this code. Okay, so this is the number of bacteria, and this is number of bacteria we by add by our hand. Okay, add by hand. Okay, so and this is on the day 0 we add one bacteria, so we there are one. Then on the day 2 we just do nothing, so the bacteria is going to be 2. On the day 3 the bacteria is going to be 4 if we do nothing. Again, let's say we do nothing and the bacteria are going to be 8. But now you can say that to make this bacteria is equal to 10, you can add here 2, right? So now this bacteria is going to be 10. But instead of this adding 2, the most important observation of this question is you can, instead of adding this 2 at here, you can add the bacteria at the day 3, right? So instead of adding the bacteria at day 4, adding two bacteria at day 4, we will just add one at the day 3, because now this one added bacteria in one day will obviously become 2. We don't have to we don't have to add two bacteria here. We can just add one bacteria here, right? So like can you so like from this we like the observation is something like this. Observation is something like this, that let's say we have let's say by one bacteria what we can get. So like we can get these numbers for like with just one bacteria, and these are power of 2. So now we have to represent the number in some number, some power of 2, right? Some power of 2, right? Because this 9, we can write this as 1 into, like we can write that as 2 into 3 plus 2 into 1, right? So like, so from this what I can say is that I will add something, add one vector, and in 3 days it is going to become 8, right? And I will add one bacteria, and after 2 days it will be 2, right? So that's it. So now just we have to find that how many numbers are there, which is nothing but number of set bits. So now the question is nothing, just the you have to find that the in number of set bits in binary representation of number n, right? That is just going to be the answer. Like what? Now how do we prove this thing? Okay, how do we prove this thing? So let's say we have to make the 10, the 10, okay. And we know that 10 is equal to uh, 2 raised to power 3 plus 2 raised to power 2, or sorry, 2 raised to power 1. I'm sorry, this was 0, okay. So we know that this is 10, 2 raised to power 3, 8 plus 2 raised to power 2, or 2 raised to power 1, which is 4. So we know that we will add one bacteria here, so that after after 3 days, here it will become 8. It will become 8, right? Okay, and I'm sorry, and uh, and like I have to add some bacteria before 1 day. So like I know that this thing here should be equal to 2. So instead of I can add this 1. So this thing will at this point will become 2. So that's it. So this thing is like this. Like if the binary representation is like this, then I will add bacteria something like this. Like this thing is the so like this thing is like the result day. Then for this, I will add bacteria 1 day before the result day. And for this, I will add the bacteria 3 days before the result day, so that by multiplying it by 2, he will become 8 after 3 days. So that's it. So like all we have to do is just find the number of set bits in this. And this thing is something like 1e9. So like we can do score something okay like this. We just take the input. Let's use just the long. The input is just the number. So we take the input and then let's say this will be our answer, which is nothing but number of set bits, and then we will run a for loop from 0 to. So we know that in the integer there are going to be only 0 to 32 bits. But let for the surety we just check till 35 bits, because this thing is doesn't going to matter much because we are using LL. Okay, so now if the like this is the way of checking this. If this ith bit is set, then we just do answer plus plus, and then we just print the answer. And there is only one test case, so we just do here the t is equal to 1. So that's it in this code. Okay, let's see one example if this is correct. Okay, what is the problem in this? Let me see. Okay, just a second. We got this is the right answer for 5. So let's just submit this thing. Oh, so I guess this is right one. Oh, now just come to the another question, which is the pretty good than this. This was something like a fundamental one, but in this is going to be quite harder than the first one. Okay, so in this question we are given the binary string of length n, and we have exactly k moves, and in one move you must select a single bit. The state of all bits except that bit will get flipped, and we need to output the lexicographically largest string that we can get after k moves. Also output the number of times you will select each bit. If there are multiple ways to do, you can print any of them. Okay, so And what is this lexicography larger? We will say later. Okay. So let's okay. So let's see what is the question. So there are key moves. There are key moves, and in one move I can do something like this. So assume that my string or the number was something like this. Okay. Now what will I do? I can select any bit. Okay, let's assume I select the second one. Okay, this one. Also this bit. I'm sorry, this bit. And now all of the other bits are going to get flipped. Only this one will stay remain. Is that okay to you? Okay. So let's say we choose like the second element. Like in the bit representation, it is going to be 0, 1, 2, 3, 4, 5, 6, and seventh bit. Okay, second element. So just let's say seventh bit. And now after operation, this thing will be changed, flipped. Only the seventh bit will remain as it was before. And now all of the other bits are just going to be changed. That is the operation. That is the operation. Okay. And now we have to find the lexicographically largest element. And how do we find this thing? Huh. So, so if you don't know what this lexicographically largest mean, it is just that if there are, let's say, two numbers, then at the first point, I'm sorry, two numbers like this one. Now, at the first point, they are not the same. They are not the same. So let's say this thing is one, this thing is one. Okay. So okay, let me be more clear. Okay. So we will just go from MSB and check this bit. Okay. Now if they are both same, then we just do nothing and move back to the next one. We will now see this second element, and if they are different, then whichever element is is bigger, so this thing will be lexicographically largest. But this thing is like, let's say we can write this as the other thing, which is just A is lexicographically bigger, which doesn't mean anything. It is just this thing. A is bigger than B in the binary representation. That's it. Okay. So that's only thing. Just forget about this thing, right? So we have to do the k operation and find the maximum element we can get in the binary thing, right? So let's say I have the element. I have the number like 00 or 01, or let's say 1001. Okay, and now k is equal to 1. I have to do exactly one operation to find the biggest element I can make from this number, right? So how do I do this? Okay, so let's say we can choose. Okay, let's just take the smaller number, right? So we can choose this one to be stay as it was before it. So the number is going to be 110. If we take the second one, then the number is going to be 010. And if you choose the third one, then the number is going to be 011, right? Obviously this thing is the largest one, so we are going to choose this one. But now there is the one most important observation. The most important observation is like I can write what, let's say this thing. So this so from this, like you know that this number is bigger than this number. So if you know that if any bigger bit is 1, then we know that we don't care about any other elements, because I know that if we can make this 1, if I can make this bit 1, then I will obviously make it 1, right? Like this is the most important observation you can say in the bit manipulation, which is like used in so much methods. Okay, just you will see that you will see in the second video how much important is this is. So there is a pattern, there is an important pattern in this, like that you will, if you have to maximize something, if you have to maximize something, you will try to make the biggest MSB equal to 1, then other element is equal to 1. So what I mean is that you will try to make something like if there are this much bits and you have to maximize the number, you will try to make this bit is equal to 1, this bit is equal to 1. After only after this you have some do something of this bit, then only you will see for this bit, right? Because you know that this is the greedy way, something like, because you have to maximize something and this value is like this, the greater than the sum of this all things, so therefore you will try to maximize this one. After this you will try to maximize for this one, you will maximize for this bit, you will try to make this one, and similar like this you have to minimize something. You will again what you will do is you will try to set this bit equal to 0, then this bit. So there is a greedy way for going like for going bit by bit. And so in this case we know that now we have to see that how many, okay, I'm sorry, like this is the number, then I will try to make this bit remains 1 after k operation, this bit remains 1 after k operation. So this is how I will going to move. Okay, now in this, how so now the question remains how to make the ith bit is equal to 1 after this exactly k operation. Like this thing is simple, right? So let's say you have some number like this, or let's say you have only one bit, something like this. So you know that if k is even, so like in the one operation it is going to be 0, and you don't select this bit. Okay, so there is a big number and there are k operation going, and you choose some other elements to remain as they were before. Okay, you don't select this one. So you know that in the this is like going to be flipped, something like this, right? This one, after one move 0, after two move. So this is the thing. Okay, now like if the k is even, the number will remain the same as it was. Like the k is 4 in this case, and now after k operation the number is as it was before any operation. Like let's so like if the number is 0, then after 2 operation it will be again 0. After 4 operation also it will be 0. After 6 operation again it will be 0, right? So this is the thing. And if k is odd, then the number will flip. Okay, but we want to maximize this thing. We want to maximize this thing, right? So let's say that I know that the case of, let's say k is odd. And I know that this bit is going to be flipped. Yet this bit is going to get flipped. And let's say the bit is currently 0. And I know that this bit is going to be flipped. So what can I do is I will just I can do that. I just don't do any operation on this. I mean I don't select this in any of the operation. I don't select this. So like if the k is odd, then automatically this thing will become 1, right? And if the bit is 1, then I know that in any one in the like k is odd, then after operation this will become 0. So so what I do is I know that like this is going to be something like this, right? Like after 3 operation this becomes 0, this bit get flipped. So if bit is equal to 1 and I know that this will become 0, so I will just choose it only one time, right? I will choose it only one time. So this bit will get flipped n minus 1 times. So which will be now remain same, because this n minus 1 is going to be even. And like if you don't understand this, so like just see the case. If let's say we just the number is 1 initially and we are going to flip this 3 times, so this 1 0 and 0. And if I just choose this one at any moment, right? Let's say I just choose at this and choose this one. So now at the third operation, while I'm doing the third operation, I choose this bit. So now I know that this bit is not going to get flipped, and this will remain the as the later one. So that's it. So I don't care about in which operation I choose this element, but I will choose. So like what I'm trying to say is that let's say we have two elements. Oh, sorry, let we have the number of 2 bits, and then I know that k is equal to 1 only. K is equal to 1 only, or let's say k is equal to 3. So I know that this one will be. So first of all, I know that. So there are 2 bits, but I know that I only care about this bit for now because this is now the leading bit. This bit is what decides, like this bit is what maximizes the answer, right? So I just choose for this one, and I know that this thing is going to be 0 now. So let's for in any operation I will choose this thing odd times, or just one times. So like what do I mean by, let's say one operation I choose the the first bit which is this one to remain same. So now the value is going to be something like 1 1. Now I know that. Okay, that's it. Now I know that after the other operation, this bit is going to be 1 only. So I don't care about this bit now. So after that, I will go to the next bit, right? And do whatever I have to do on this next bit. And that is how I will greedily decide. So like how the answer would look like is something like I have the list of some bits and some k. Let's say some k. Okay. I will go at this bit. Now I will say that after k operations are doing after done, what will be the value of this bit? And if this bit is 0, then I know that I will choose this bit exactly one time, right? Exactly one time, so that after k operation this bit get flipped and this bit will be 1. Okay. So what I do is that I just have this one. I don't care if it is even or odd, but I will just check that after k operation, what will be its value? Okay, and then if the value is going to be 1, then that's what I want, so I will not choose it in any operation. But if this thing is going to be 0, then I will choose it. After that, I will go to this element, get this element, and check for this. And if still I have some of the k remaining, I will just going to add for this smaller ones, because I know that I cannot change this in this bigger ones. Let's change in this one. I don't care about whatever the change happen in this bit. Okay, so that's it. That was it. So what do I do is something like this. I just take the int n and k. Then we can just take the input as the string, although this are the bits, but we just store them as the string, and just take the input and k and the string. After that, what we'll do is run a loop. Okay, what do I have to? Okay, I have to give answer something like this, and also the something of this. Okay. So I should have a vector of n which will store the answer, and that should be of length n with this 0 initially, and I just run a loop on all of the elements, and then now I have to check what its value be after n operation, sorry, exactly k operation. If I don't do anything, if I do nothing, like if I do nothing, or if I just don't select this ith element. Okay, what is okay? Oh, sorry, I just used the snippet so much, so I just forgot this thing. Right, so now I have to check what its value be. So let's say ll val, and now I know that if the k is odd, the k is odd, and let's say that the value of this string minus a, sorry, minus 0. So this is the way to get the numerical value from the string. I hope everyone knows this thing. If don't, you just remember this. Okay. So if the k is odd, and we know that in the this thing, the bit gets flipped. So if this thing is 0, then I know that value is going to be 1. Else if else if this is, just paste this thing. Else if, so there is the easier way to do this, but let's just do this manually. Okay. So we know that if the k is odd, then this bit is 1, but I know that it is going to be get flipped. So val is equal to 0, else if k is, I know that my k is even in now, and I know that now the bit doesn't get flipped, so val just stays as it was before, str of I minus 0. So that's my bit. That is my bit. Now, sorry. Now, if if the string is sorry, if the value is 0, if the value is 0, then I will just choose this I one time to just remain as it was before, and I know that now this thing will get flipped. Now the value will get 1. So, but for that, like there should be some uh, operation remaining, right? There should be some operation in which, like, I have used all of the operation in the leftmost thing, and now I will come to some point, but I don't have any operation. So I can do anything, but so therefore val is equal to 0, and I have some operations remaining. Then what I will do is, then now this ith bit will become 1, and but I know that one operation is used. Also I have to store this thing in the answer, so this thing gets, this is clear. And now all the other things, all the other extra things will now just I will just dump this into the last element. That's it. Now I have to return the print the string endl and print the answer array for in I from 0 I less than n plus plus just print the answer of I and that's it. I have to use space here. So let's try to run this code. Okay, so yeah, there is some problem in this case. Some problem. What is the problem in my code? So I take the input and the string and k is correct. Answer is correct. So I guess this thing is somewhere wrong. Okay, I have to see. The k is odd. Okay, okay. Oh, so the I don't have to. Okay, so I just did a smaller mistake in remaining k is equal to k and now or like operation used. Okay, used operation which is 0. This thing was sorry. I shouldn't use the k which I use in this checking thing. Okay, but that was my mistake. I just used that how many operations are used currently, and if the operation of that used is less than k, then I will do this and just do this plus plus. So that's it. And, and all the other extra remaining operation which are k minus used, I will just dump this here. I guess that's it. So again, there is some problem. I'm not doing k minus minus. So like this thing is 1001 and I don't flip here. Okay, okay, yeah, yeah. Let's just say else. I know that it is 1, so str of I is equal to 1. I know that this thing is already 1. Yeah, just a second. If if the well is already 1, what I'm saying is that if the value is already going to be the 1 after the operation, I know that I have to change this thing. So I will just do this. That's it. So let's say in this question, what will happen is okay. I also I have to flip this thing. Flip the last is that okay? Sorry, I just forgot one thing. So for the last element, I am just dumping this much values, right? I am dumping this much value. So after I flip this much time, I know that the element as this value will also be get flipped. So I have to use this thing. Okay, so now if k minus used is a odd thing, then I know that my final value of this answer is going to be flipped. And how it is going to be flipped. So if the value at this n minus 1 was 1, then it will be 0. Else if it was 0, then it is going to be 1. So that's it. Okay, so that is the thing, right? So now you can see that these answers are correct. Okay, these answers all are correct, and you don't care about this thing. These are like any of the valid answers are correct. So which was the question? Name was Bib Flipping. Yeah. Sorry, there is some problem in my solution. So the answer is wrong in the test case 4. What is the problem? Let me see. So the fourth test case is something like this. And okay. I just again did a small mistake. Else string of I is, yeah, going to be 0. That was the error in my code. If it is going to be 1, then it is 1. Else I will make it 1, and if I cannot make it 1, then this thing will happen, right? So this thing is also in the else if. So that's it. Now let's see. Hope it is correct. Again, the wrong answer. Where is the problem coming? Like in the test case 5 again, the string is not matching. Why? Like the n is 12. The answer, my output is this. His output is this. So what is the problem? I cannot see it. Like in the fifth test case, which is this one, and my answer is this one. Somewhere I am not flipping my bit. Is this the okay? So let me just think for a second. I know that this bit should get flipped. Should be get flipped. That's it. What I'm doing is I'm doing answer of I plus equal to remaining ones. And if this is 1, I make it 0, else I make it 1. If this k minus u is equal, is equal to 2, is this thing happening? Because if this thing is even, I know that I don't have to flip these numbers, and that's correct. I will just add it in the answer. I will not flip this ith bit, which is this. Just let me think for a moment. As value, then I just check that what is the, like if the key have 2 and then this will get flipped, this will be 0 or this will be just remain as it was, then if L is equal to 1, this thing is going to be this one, else if L is equal to 0 and used is equal to 0, then I'm going to flip this one and have answer as this. Let's just we just don't care about the last thing now. Let me just do this, right? And let's see what we get for the fifth bit. So like I know that for fifth bit, what is happening? Just give me a second. So in this fifth bit, I know that this bit should be equal to 1 because after the even number of flips, so like this thing is 0 and after odd, this thing is already going to be 1. So like I will check this and the string is equal to 0. This value will, this thing will be val is equal to 1. And now I will use the remaining one in this thing. And if the remaining thing is that I will flip the string. So like what is the problem till here is what is the string till here? Let's just try to print this. Okay, here. See out the string and also print the k minus used, which is the which will give me the parity. There is some okay. Oh shit. The problem is okay, this one. Now what we do is we just see the case for this fifth one. And now this thing okay now okay shit. So like I guess the yes now it is correct. Now it is correct because so I guess the problem was here because I just added an extra space in this. It was a tough debugging question I made. It was, I guess, I hope that's it. That was the problem. Hmm. Taking so much time. Okay. Like the test case one is correct. I hope yeah, it is correct. Okay. So taking too much time. I guess that is the other contest is also going on. So like many people are submitting now. So there is a long queue formed. I guess let's just wait for now. Okay, so now this thing is working. Oh, again taking so much time. Yeah, and this gets accepted. So I get that that was it for now. These are the we talked about all the fundamental things in this, and from the second video this will be our like main video, and we'll talk about the main list of patterns and also the amazing patterns and this small topic which is using bits and sets. We will also do the union and intersection and all of the things with bit. And I guess that was it for now. So let's meet in the second